This is an Atwood machine that has friction in it. In the figure we see one block that's on an inclined plane. It's connected to another block through a wire. That second block is hanging off the edge vertically. We have an upward force pushing on the other block. And we want to know the tension and the acceleration of the system. So in this case, if we want to know the tension is a force. The acceleration is related to the force by Newton's second law. And so if we look at the forces acting on these objects, we'll be able to find the force of the tension, we'll be able to find the acceleration of the system from those forces. So we will begin by looking at the first block. We have an angle beta there. We have the block. And that block has a force of gravity. We'll call that gravity M1G. The block is connected by a tension. There is a normal force pushing the block up. We'll rewrite our force of gravity as components. And in this situation, different from the other Atwood machines we've seen, it's clear what direction has to happen here. The rope can only pull downwards, it can only pull towards the middle, so the rope is going to be pulling this block downwards. Gravity is going to be pulling this block downwards. And so if this block is moving, it has to have a force of friction that's going upwards. Basically, that force of friction is either a static force. If that force of friction is so great it can overcome the force of the tension and the force of gravity, it will hold this one block in place. If the static force is not sufficient, then we'll begin moving, we'll be in the kinetic regime, and the kinetic friction will slow this block down as it slides. But in this situation, there's really only one direction of motion possible. So we'll go ahead and put that force of friction in our free body diagram because we know what direction it has to point in based on the layout of the system. And again, to keep our pluses and minuses correct, we will write our axes for this block on an inclined plane. We'll also do a free body diagram for M2. We'll do a more traditional free body diagram because it's hanging up and down. We know that it has gravity acting downwards on it. We know that we have tension acting upwards. And we also have this applied force. We don't know the relative sizes of it, so we won't worry about that, about being too correct in our free body diagram, other than to keep it to keep them in the correct direction. And then our last point here is that with this system, really what has to happen is this block either has to slide down the ramp or it has to stay put. It's technically possible, and we would see that in the calculations. If you pushed really hard underneath this block, the force could lift that block, and then you would lose tension in the rope. In that situation, you would have to be pushing harder than the weight of that block, and we can see that the block weighs 2 kilograms. It's going to have a weight of about 19 kilograms, and we're only pushing up with 6 kilograms. So there is a net downward force. This block then should be going downwards, and this block should be going downwards as well. That's our assumption when we put in our direction of our frictional force, and that's really the only direction that makes sense in this situation. So what we'll do now is use Newton's second law. We will write equations for the forces. Looking at this block, we're going to be moving along the face of the inclined plane. we see that gravity is making us go down and to the right, so that's a positive force. Tension is pulling us down and to the right, so that's a positive force. Frictional force is to the left, so that's negative, and that is the mass times acceleration. This frictional force we know will end up being the coefficient of friction times the normal force, and we know that the normal force will be balanced out by the perpendicular component of gravity, and we'll get to that in just a minute. When we look at this other block, we know that the acceleration has to be downwards, we said, and so in this case we have the applied force is upwards, that's positive, the tension is upwards, so that's positive, gravity is downward, so that's negative. Those are all the forces. That equals MA, but MA is downward, so that's negative as well. We'll rewrite this equation and clean this up a little bit. We're going to start with the coefficient of static friction, because we're going to make sure that the system is actually going to move, that static friction isn't so much that it will actually stop the system from moving at all. This is the coefficient of friction times the normal force. The normal force is being balanced out by the perpendicular component of gravity. Looking at the other equation over here, we're going to multiply through by a negative sign because we want our accelerations to both be positive, and the other thing, we want our tension here to be negative so that it will cancel out the positive tension in the other equation. So here we have one equation for block 1, we have another equation for block 2. We have just moved them around a little bit, set them up nicely so that we can add them. When we add them, we see we have a plus tension and a minus tension that will cancel. What we see here again is that this is an external force pulling us down, that's an external force pulling us down, so we should be pulling down, we should be falling downwards. Friction is pulling us back up and is slowing down the acceleration. This applied force is resisting our motion and slowing down acceleration as well. And so when we find the acceleration, as we've seen before, we will factor out a common acceleration. And we can find from this equation, looking at this value, what this tells us right now is that even if we assume the greatest static friction possible, we can plug in numbers everywhere and the acceleration would come out to be about 4.7, meaning we are going to accelerate downwards like we thought we would. If the external forces, the forces of gravity, are big enough to break static friction even at the maximum amount of static friction, that means we would start accelerating and we would start moving. That means that the static friction would break down, and actually what we would have here is kinetic friction instead. So kinetic friction is even less. That means it's even less of a drag on these external forces, and so our acceleration will be even greater. And so in this case, our acceleration we have a full equation for our acceleration. We know this equation is going to come out to be positive, meaning that our acceleration is actually going the way we believe it ought to be going. And we can plug in the numbers. And we find that the acceleration, when we've switched to our kinetic regime, the acceleration actually comes out to be 5.6 meters per second squared. And so in this situation, we started out, due to the arrangement of the system, we could assume the direction of the accelerations. We've then tested static friction to see if the external forces were enough to break static friction. They were, because our acceleration came out to be positive. So if the external forces are enough to get the object moving, then we'll be in the kinetic regime, and we recalculate. We basically plug that last number in the kinetic regime. That's the acceleration of the system. Once we know the acceleration of the system, we can go back and find the tension. Basically, we could use either single equation. This situation is much simpler, and so it's easier to say that the external force plus tension minus m2g equals negative m2a. Basically, this is saying that 6 plus the tension minus 2 times the gravity is equal to negative 2 times 5.6, and we can solve for that as well. And it turns out here that the tension is equal to 2.4 newtons. That's a pretty small amount, but that makes sense. Both blocks are going to be wanting to fall downwards on their own due to gravity. The one falling straight down ought to be going faster than the one falling, sliding down the inclined plane, but in either case, there's an applied force slowing this guy down, there's frictional force slowing this other one down, and so the tension is just evening out. It's enforcing that acceleration constraint, that they should go together. But since both of them have gravity accelerating them, both of them are being slowed down a certain amount by applied forces, by friction, or by an applied force, it would make sense that they're moving almost together anyway, and so just a little bit of tension is needed to finish up balancing those accelerations.